Hello and welcome to this lecture. In this lecture, we are going to see yet another wonderful application of linear algebra and symmetric matrices, which is in a completely different area. It's an area called graph theory, and we are going to talk about graphs and adjacency matrices. So hopefully this gives you a flavor and power of linear algebra, right? So it has applications everywhere, wherever you can think of. Linear algebra has applications. Okay. So what is a graph? A graph basically has two sets in it. First is called a set of vertices or nodes. Okay. So we'll usually denote it V, and it goes from 1 to n. Okay. The next is a set of edges, okay, which I will call E. These edges are basically pairs of nodes. Okay. So you have n nodes 1 to n. I pick any pair of nodes and I call that an edge. Okay. Maybe 1 comma 2, 1 comma 3, 4 comma 6, anything like that. Any pair is an edge. So notice I have m edges here, n nodes and m edges, right? The first edge is I1 comma j1. This I and j belong to this guy and they cannot be equal. Okay, so I'm going to take that they're not equal. So you have m edges and n nodes. Okay, so in this way the graph looks very boring and tiring. It's just some big notation with sets and all that. It turns out the graphs can be plotted as a diagram. I mean, you can draw a diagram of a graph, make the nodes as points and then edges as lines connecting those points, and you get really interesting structures. Okay, so let me show you that to you with an example. So I'm going to pick n equals 4. So my V becomes 1, 2, 3, 4. And my edges are basically one of 6 possibilities, right? Edge could be 1, comma 2, 1, comma 3, 1, comma 4, or 2, comma 3, 2, comma 4, or 3, comma 4. One of these 6, any of these subsets, any subset of this set can be my edge. I may have all of them being an edge, maybe none of them being an edge, 3 of them, 4 of them, like that. So let me show you a few examples. The first example is m equals 6, which means all my edges, all my possible edges, E equals this entire set, all 6 are there. So how will I draw it? I draw my 4 nodes. These are my 4 nodes, 1, 2, 3, 4, okay? And my edges are connecting the 2 nodes that are in there. Okay, so 1 comma 2 is there, so I connect. 1 comma 3 is there, I connect. 1 comma 4 is there, I connect. 2 comma 3 is there, I connect. 2 comma 4 is there, I connect. 3 comma 4 I connect. So everything is connected. So for that reason, this graph is called a complete graph. So this is one example of a graph. Hopefully you see that. Okay, I could have m equals 5. So maybe this 1 comma 4 is not there, right? 1 comma 4 is not an edge in this another example of a graph. So all the other lines are there. This one line connecting 1 and 4 is not there. Okay, so you can create many more graphs like this, right? You can have m equals 4, which has only these rectangle type of connection. This is called a cycle. When you have a cycle, a closed loop like this, it's called a cycle in a graph. Or you may have m equals 3, only 3 edges, and this is just 1 comma 2, 1 comma 3 and 3 comma 4. Only these 3 edges are there. Okay, only no other edges there. This is in fact called a tree, okay, or a line in this case. Okay, you may have m equals 2, which is just 1 and 2, 3 and 4, no other edges, okay, only 2 edges. Or you can have m equals 1 with just one edge, 1 comma 2. In fact, there are many more with m equals 2, right? I may have 1 comma 1, 2 and 1 comma 4, or 3 comma 4 and 3 comma 2. Many more are there. I'm just giving you one example. M equals 1. And the last one is m equals 0, which is no edge. It's only one graph like that. It's 1, 2, 3, 4, and it's empty. Okay, so this kind of pictures is what makes graphs very interesting. Okay, so you can define nodes in a setup that you have in whatever system you're looking at, and then you can connect them with edges if they have some relationship or if they are sort of close to each other or something like that. Okay, so this is what makes graphs very powerful. So this particular type of definition I'm doing has some names like undirected, no self loop, single edge. Okay, so I won't pay too much attention to it. As far as we are concerned, this is how graphs are defined. Okay, so I don't have a self loop. Okay, I to I, there's no connection. Okay, and there's no direction. If I have 1 to 2, 2 to 1 is also connected. I won't put direction on it. So this is the special case of graph. There are also various other cases. Okay, so graphs are everywhere. Okay, I don't have to convince you. You might know already, but then let me again repeat. Graphs are everywhere. Okay, so here is a circuit. You might say, where is a circuit and a graph related? But it turns out I can define nodes. Everywhere there is a junction between 2 elements, right? I can define a node. So this circuit actually has 4 nodes, 1, 2, 3, 4. Okay, so maybe even lesser in some things we don't distinguish the nodes here, but here in this graph I may want to distinguish between the nodes, between elements. So 1, 2, 3, 4. And then what can I say? The edges are basically the 1 comma 2 edge has an inductor L. 1 comma 4 and 3 comma 4 has a capacitor C in it, and then 2 comma 4 has a capacitor C1 in it. Okay, there's no other edges. So there are 5 edges in this graph. Okay, Okay, so notice how a circuit can be converted into a graph. In fact, all circuits that are represented in a computer and simulated are represented by graphs like this. If you're doing a very large system integrated VLSI type system, and you have a very large circuit, even there, ultimately in the computer it represents it as a graph. A lot of graph theoretic ideas are used in EDA tools and all that. Okay, so in fact graphs are everywhere. There are networks like this, no, just nodes connected, cities connected by roads, that's a graph. Cities connected by trains, that's a graph. Airports connected by flights, that's a graph. Internet, computers connected to each other, it's a graph. LAN, it's a graph. Wi-Fi is a graph. Everywhere you'll have graphs. And today the graphs abound. This, web pages, www is in the graph. Everything is represented as a graph. So graph theory is really powerful. And there are various types. You may have directed and undirected edges, single edge or multiple edges between a pair of nodes. There may be self loops, may not be self loops. All these are various things. So graphs are indeed everywhere. So we're going to study how linear algebra connects to graphs. Okay, so how matrices enter the picture here. Okay, so all that comes from this notion of an adjacency matrix. There are also other matrices that people define around graphs, but I'm going to focus on this adjacency matrix and what properties it has. Supposing I have a graph G, which is V comma E, and it has n nodes and m edges. Okay, some pairs of nodes are connected, and that's forms my m edges. If I comma j is an edge, we usually say that vertex I is adjacent to vertex j. Of course, vertex j is also adjacent to vertex I. I and j are adjacent vertices, okay, because they are connected by an edge. I can sort of hop from one edge to the other along the edge in one step. Okay, so that's why they are called adjacent. They are also called neighbors. There are various terminologies in graph theory for how an edge connects. Okay, so the adjacency matrix of the graph G is, I will denote it usually as A. It's an n cross n matrix. Okay, so I have n vertices. So it's n cross n matrix, and the ijth element is very simple. If I comma j is an edge or j comma I is an edge, I will make the ijth element as 1. If I comma j is not an edge, which clearly means that j comma I is also not an edge, I will make the ijth element 0. Okay, very simple definition for the adjacency matrix. Okay, n rows, n columns. Each row corresponds to the vertex, each column also corresponds to the vertex. If that row and column are connected, I will put a 1 in the I comma jth element, and j comma I also is 1. Otherwise, I will put a 0. Okay, so that's the idea. Okay, so it's a complete representation of a graph, and this is how, as matrices, graphs are represented in computers. Okay, so that's why adjacency matrix is very important. And here is an example just to show you how it works. I picked n equals m equals 4 here. This is a slightly different graph, okay, from what I showed before. This is G. So I have 1, 2, 3, 4 representing the 4 nodes here, 1, 2, 3, 4 representing the 4 nodes here. The first node is not connected to itself, 0, okay, and it's connected to 2, so 1. It's not connected to 3, so 0. It's connected to 4, so it's 1. So likewise, every row is put up. Look at the third row. Okay, third node 3 is only connected to 4. It's not connected to anywhere else. So you have 0, 0, 0, 1. Likewise, you have the whole adjacency matrix A. Here is an important observation property for the adjacency matrix. The adjacency matrix is symmetric. Okay, so notice how symmetry comes in wonderfully, and it has 0 on the diagonal, right? So on the diagonal it has 0 because I didn't allow self loops in my definition. So 0 on the diagonal, and it is symmetric. Okay, symmetric because ij and ji are connected. So it's undirected, right? Ij and ji are the same, so it will always be symmetric. Wherever you have a 1 in ij, ji will also be 1. If ij is 0, ji will also be 0. Okay, so that's the nice symmetry property for the adjacency matrix. Okay, so one of the things to worry about in a graph, supposing you have a transportation network, right? So you want to go from one city to another city. It may be over multiple steps on a big transportation graph. Okay, but you may ask a question: how quickly can I go from one city to another? How many hops do I have to do? How many steps will I need? Like that, you may ask some questions, right? So when you have a graph, questions about paths in the graph, going from one node to the other, ultimately through many edges, is an interesting and important question. Okay, so one question you may ask is: in how many ways can you go from vertex 4 to vertex 8? Okay, 4 and 8 are not directly connected, so you cannot do one step, but you can do 2 steps, right? Look at this. You can go to 2 and then to 8. Okay, but you can also do 3 steps. You can go to 1, 2, and then 8. You can also do more interesting stuff, right? You can do 3, 6, 8. It's again possible. You can do 7, 5, 6, 8. Okay, so looks like there are multiple ways in which you can go from 4 to 8. Okay, so in every step you can go to an adjacent vertex. That's the main idea, and you can hop, go to the vertex you desire. How do you count the number of paths? Number of paths between 4 and 8 in so many steps. How do I count that? Turns out adjacency matrix has the answer. Okay, so the property is very, very interesting and simple. If you have a graph G with an adjacency matrix A, the ijth entry of A power k is the number of paths from vertex I to vertex j in k steps. Okay, so let's put k equals 1, right? So A, the ijth entry of A is the number of paths from I to j in one step. Okay, so if there is no edge, that is 0. If there is an edge, it is 1. So there's one path. Now if you do A square and look at the ijth entry, then that number is actually the number of ways in which you can go from I to j in 2 steps. Okay, so this is actually not very hard to prove, but I'm not going to prove it for you. We'll accept this as a result. It's quite reasonable to see why this should be true. Okay, the ijth entry of A plus A squared plus A power k is the number of paths from vertex I to j in less than or equal to k steps. Okay, so this is another property, right? So if you have A power k being in k steps, if you add up everything from A to A power k, it will be the total number of paths in less than or equal to k steps. Okay, so this is a very, very powerful and interesting property of the adjacency matrix, and how matrix multiplication ties up with the paths. Okay, so A into A squared gives you the number of paths from I to j. Think about how you may prove it. You'll have proofs in the internet if you're interested in the proof, but it's sort of intuitive. You know, A is 1 step, A square is 2 steps, A power 3 is 3 steps, and all that. So matrix multiplication and with adjacency matrix gives you this powerful property. Okay, so and in fact these are all powers of a symmetric matrix, no? So symmetric matrix, we know you can use the spectral theorem and the decomposition. So powers are very, very easy to evaluate as well. Okay, that's that. Okay, so let's do a few examples. So let's go back to this example we had here, 1, 2, 3, 4 with this connection. A was this. If you do A squared, you get 2, 1, 1, 1, 1, 2, 1, 1. Notice in A there is no direct connection from 1 to 1. But if you look at A squared, you can go from 1 to 1 in 2 ways. So you can do from 1 to 2 and then back to 1 again. 1 to 4 and then back to 1 again. Okay, so there are 2 ways. In 2 steps you can go from 1 to 1. Okay, in 1 step you can't go from 1 to 1. Okay, from 1 you can only go to 2 or 4. Okay, so likewise every other entry. So in fact 3 paths from 4 to 4 in 2 steps, 4, 1, 4, 4, 2, 4, 4, 3, 4. Okay, look at the 0 here. From 3 to 4 you can't go in 2 steps. Okay, you can go in 1 step, but you can't go in 2 steps, because from 4 you'll have to go off somewhere else. Okay, so that's one thing. Here's another very interesting property here. This 1, 2, 3, 4 cycle graph that we had, right? It has a adjacency matrix which looks like this: 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0. You may want to check this. It's a very interesting little, it's also circulant, right? It's a very interesting little matrix here. Now, if you do A squared, you will get 2, 2, 2, 2 on the diagonal. Okay, so you can see from any any node to itself, there are 2 paths in 2 steps. Okay, 2 to 1 back again, 2 to 3 back again, like that. But if you do A power 3, very interestingly, it goes back to 0 again. You can never go from 1 to 1 in 3 steps. Okay, you can go 1 to 2. If you go off to 2 to 3, then you can't go to 1. If you go back to 1, you'll have to leave 1 in the next step, right? So from 1 to 1, there is no path in 3 steps. Likewise, from 2 to 2, there's no path in 3 steps. But if you do 4 steps, you will again get something from 1 to 1, 2 to 2, 3 to 3, 4 to 4. Okay, so it's very interesting how these things work. So, so from I to I, there are 2 paths of length 2, but no path of length 3. In fact, there are very interesting properties like this that you can see when you look at graphs of this nature. Okay, so this gives you a sense of how to connect paths to the powers of the adjacency matrix. Okay, you can also do spectrum for a graph. Okay, eigenvalues for a graph, right? So the eigenvalues or spectrum of a graph are basically the eigenvalues of its adjacency matrix. You take the adjacency matrix, right? It has eigenvalues. It's a symmetric thing, so spectrum is in fact real. Okay, and the eigenvectors are basically orthonormal basis itself is there. So the eigenvalues of A are also called the eigenvalues of the graph. Okay, so let's take it as the eigenvalues of a graph. Here's a couple of examples. If you take the complete graph, okay, if you take the complete graph, 1, 2, 3, 4, all the edges are there. Here is the adjacency matrix. Do you agree? There is no connection from any node to itself, but all other connections are there. Okay, so if you think of the spectrum of this, what are the eigenvalues of this? Okay, what is eigenvector eigenvalue? So you remember the tricks I told you. You can look at the row sums. The row sums are all the same. So 1, 1, 1, 1 will be an eigenvector, and the eigenvalue will be 3, isn't it? 1, 1, 1, 1 will be an eigenvector, eigenvalue 3. The other eigenvectors here are a little bit tricky to figure out, but once you figure it out, you will see where they come from. Look at this guy, no? 1, -1, 0, 0. Okay, 1 minus 1 0 0 is actually an eigenvector. If you do 1 minus 1, you will end up getting minus 1 1 0 0. Okay, so it's an eigenvector with eigenvalue 3. So once you identify this, you can also do that for the second one. Okay, 0 1 minus 1 0 is again an eigenvector. It's got an eigenvalue minus 1. Likewise, the last one 0 0 1 minus 1 is again an eigenvector with eigenvalue minus 1. So you notice the orthogonality property. Okay, so for 3 and minus 1 it's always orthogonal, but between minus 1 it is not orthogonal. So you can take these guys and do the Gram-Schmidt process and get an orthonormal basis if you like. Okay, so I'm not bothered about it, but this is at least an eigenvector eigenvalue combination. So let's go back to our cycle that we had here 1 2 3 4 and ask about eigenvectors eigenvalue. This is circulant, so you can use the circulant matrix ideas, but then you will get some complex stuff. It's a little bit confusing. So what you can do instead is just look at this and guess the eigenvalue. See, first of all 1 1 1 1 will be an eigenvector with eigenvalue 2, and then notice that first column and third column are the same, so null space is there. Likewise, second column and fourth column are the same, so null space is there. There is a null space of dimension 2. So you will have two vectors of eigenvalue 0, right? 1 0 minus 1 0, 0 1 0 minus 1. This is also an eigenvector. It's got an eigenvalue 0. Okay. So notice all the orthogonality. This is also orthogonal here, so it's very nice. Now trace is 0. So if you have 2 0 0 as 3 eigenvalues, the last one should be minus 2. So minus 2, in fact, you can see that 1 minus 1 1 minus 1 is actually a eigenvector here with eigenvalue minus 2. Okay, so you can check all the orthogonalities. This is an orthonormal set, sort of related to Hadamard also. So you get this as the eigenvalues, eigenvectors for this graph. Okay, so that's another example. Okay, so how do you make use of these eigenvalue eigenvectors? So it turns out I'm going to show you one example where the eigenvalues eigenvectors of a graph or the adjacency matrix play a crucial role in graph theory. Okay, so that is in finding out something about bipartite graph. So let's quickly go through this. What is a bipartite graph? Okay, the graph has nodes and edges connecting all over the place. It is said to be bipartite if you can take the vertices and partition them into V1 and V2. Okay, you partition them and then edges should only be from V1 to V2. There should be no edges within V1, no edges within V2. Okay, so that is the most important property of a bipartite graph. Okay, V1, V2, two partitions, all edges are only across the partitions, nothing inside V1, nothing inside V2. That's called a bipartite graph. Okay, so any bipartite graph will look like this. There are first S vertices. I am drawing the first S vertices as belonging to V1, and S plus 1 to n belongs to V2. And all edges will be from this part to this part. There will be no edges here, no edges within here. So if you draw the adjacency matrix, what will happen? The adjacency matrix will go n by n, and the sth column and sth row will be here. Now from 1 to s to 1 to s, there are no edges. So this entire block is 0, 0, 0, 0, 0, 0. From here 1 to s plus 1 to n, there may be edges. So that may be some matrix B. Okay, so this will be a S by n minus s matrix. Now this part will be B transpose. There is symmetry, right? So you'll have B transpose here for the last part here. And this last S plus 1 to n, S plus 1 to n has to be 0 again. There's no connections here. So notice how this adjacency matrix has this wonderful structure when you have bipartition. Now you may wonder, why should I have 1 to s here and S plus 1 to n here? That may not be true, but it turns out you can renumber the vertices in any order, and so that you will end up getting this structure. Okay, so that's also possible, right? You just simply renumber them so that V1 becomes 1 to s and V2 becomes S plus 1 to n. But this may not be very easy, but if you do that, then you will get this kind of a structure. Okay, so what is nice about bipartite graph? First thing is about paths. Okay, so there's something very curious about paths in bipartite graph. If you look at path from I to I, okay, if you look at path from I to I, it's possible for an even number of steps, but it is not possible for an odd number of steps. If you start at I, you cannot come back to I in an odd number of steps. Why is that? Because in an odd number of steps, you will be in V2. If you start in V1, in an odd number of steps, you will always be in V2. You would have gone to the other side. You can never be back in I. Okay. Likewise, if you start at V2, in an odd number of steps, you will always be in V1. Okay. So you can't come back. So path from I to I is not possible for odd steps. What does that mean for the adjacency matrix? A power k for odd k will have all diagonal entries or I comma I entries as 0. Okay. So this is an important property of bipartite graphs. No odd number of path, odd numbered paths, odd length path from a node to itself. Okay, So this is, here is another result. This is a very surprising result. So the converse is also true. For a bipartite graph, this property is true. Or the converse is also true. What is the converse? If a power k for all odd k has diagonal entries as 0, then the graph is also bipartite. Okay, the reverse is also true. If you have an adjacency matrix and if you raise it to the power k and for all odd values you are seeing that the diagonal is 0, then it is automatically bipartite. Okay, so what does this mean? This seems like a slightly complicated condition. It turns out this has a very nice impact on the spectrum. Okay, so here is the spectrum. So if you look at the spectrum of a bipartite graph, if lambda is an eigenvalue of a bipartite graph, then minus lambda is also an eigenvalue. The proof is actually quite simple. Let's look at the first partition as 1 to s, another partition as plus 1 to n. So if lambda is an eigenvalue, the eigenvector v can be split as v1 to vs and vs plus 1 to vn. I'm going to call this as u1 and call this as u2. Okay. Now av equals lambda v. Now a is nothing but 0b, b transpose 0, right? So now 0 is a big block 0, okay, s cross s 0. This is n minus s cross n minus s 0, okay, remember that. Okay, so it's a big 0 here. Now av equals lambda v can be split as into u1, u2. If you multiply, now this is a block multiplication, so this will be 0, you will get b u2 and b transpose u1. Okay, so think about this a little bit, and this equals lambda u1 u2. Okay, so now in the proof what you can do is you can look at this same matrix multiplying u1 minus u2, you will get minus there and then plus here. Now if you look at this guy, b u2 is u1, so you will get lambda minus u1 here, b transpose u1 is u2, so you will just get u2 here. So what you have here is lambda minus u1 u2, and this here you have u1 minus u2, so you can pull the minus outside and write it as minus lambda u1 u2, so minus lambda is an eigenvalue. So proof went really quick. So basically the point is, if lambda is an eigenvalue of a bipartite graph, minus lambda is also an eigenvalue. So let's now ask the question, can we use the spectral property to find out if a graph is bipartite or not? You might say for small examples it's easy, but for large examples it can become really hard. If you have like n equals 1000 and m is some 500,000 or something like that, really large, how do you find the graph is bipartite or not? It's very hard to try all possible partitions. So it turns out this converse of the previous result is also true. Okay, if for every non-zero eigenvalue lambda of a graph, minus lambda is also an eigenvalue, then the graph is bipartite. Okay, the reverse is also true. If you find the spectrum and if you see the eigenvalues are occurring as lambda minus lambda, the graph is bipartite. Okay, so there's a proof for this. I'm going to quickly skim through this. Basically the point is, if you have a having eigenvalues lambda 1 to lambda n, a par k also has eigenvalues lambda 1 per k to lambda n per k. Now if k is odd, lambda 1 per k plus lambda n per k will be 0, the sum. The reason is lambda and minus lambda are pair of eigenvalues, right? So whenever you add here, it will be 0. But the sum of eigenvalues is the trace. Trace is the sum of the diagonal elements. Sum of diagonal elements is 0. But now all diagonal elements are positive. Their sum is 0. So there are no paths from I to I for all odd k, and that makes the graph bipartite. Okay, so it's a wonderful relationship. I just want you to think about what this means, right? So we had a graph. We related it to an adjacency matrix which was symmetric. Then you have an eigenvalue property. Now that spectrum is telling you something about the graph. The graph is bipartite if the eigenvalues occur as lambda and minus lambda. Wonderful result, isn't it? So here's an example just to illustrate how to use this. So if you look at the complete graph, it is not bipartite, right? So it's quite easy to see the eigenvalues. We just derived 3 minus 1 minus 1. There is no minus 3 as eigenvalue. There is no 1 as eigenvalue. So clearly not bipartite. Okay, lambda and minus lambda have to be eigenvalues. Look at this guy, this cycle, right? 1, 2, 3, 4. 2 is there, minus 2 is also there. So this one is bipartite. Okay. So, but here in the matrix, it's not clear, right? It's not like it's not in the B transpose form. Okay. What is V1 and V2? It's not very clear. It turns out if you exchange 2 and 3, it will become very clear. If you exchange 2 and 3, you will get 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. Try it again. Like just put this graph here and put it there. You get it back into the same position. Okay. So you can identify it bipartite, not bipartite, just by looking at the eigenvalues. And in fact, you can do more, right? So what I've told you is only this. You can do much more. There's further study. If you're interested, you can look it up. There are easy methods to identify the bipartition using eigenvectors and eigenvalues as well. Okay, so hopefully this gave you a flavor of the power of linear algebra, the variety of applications of linear algebra, graph theory, which it started in some combinatorial way with sets and all that, has an adjacency matrix which is symmetric, and it gives you eigenvalues and eigenvectors. And those eigenvalues, eigenvectors tell you something about the graph itself. Wonderful, isn't it? Okay, thank you very much.